All right, cool. This brief was handed down to us from Cyber Development Unit 1 in 2019, which I've been informed does not exist anymore. So that's sad. Operating systems. Operating system. What's a Dell? A Dell is not an operating system. So what are operating systems? So what are some of the operating systems that you see here, like that you could name out? Windows, Android. So Apple's not technically an operating system. Mac OS is. What's the other one? It's on your phone. iOS. There you go. And then, anybody know what this penguin is? Linux, right? So Ubuntu is the Linux operating system. It's a distribution of the Linux operating system. So there are more operating systems out there. There's also Unix operating systems, which is Linux is basically off branch of that. And then there's multiple distributions of Linux. So they call them flavors essentially. So you have things like Ubuntu, Kali, Debian, and then there's other ones that run just Unix, but they don't adhere to Linux. So things like Red Hat or CentOS or CentOS. Yeah. So we don't care about that. Basically, the idea is to understand how OSs work at a high and low level. We'll briefly go over process and memory management, but really we're talking about operating systems. So a little background. You can see basically started in the 1940s where the first computers were programmed, and they were programmed directly with machine language. So that's like the hex characters, basically, right? Not fancy words that we get to see, and they were called mainframes, and they were built that way. 1948, the first assembler was made, and so you no longer needed to write machine code. So essentially, the assembler assembled it into machine code form. Super cool. 1950s, various early OSs came out. You had Lion Electronic Office, MIT's OS, General Motors OS. Um, there was the first commercially used OS, which is GM and AAIO. And then in the early 50s, compilers with higher level languages began being developed as well, making OS development easier. Mid 1960s, multi-programming capabilities developed for OSs. So essentially, you could multitask on a computer. So a lot of times, it was just like this one computer, and you're like reaching out to it, and everybody's sharing the resources on this computer. And so now the computer can do multiple tasks at the same time. Multiple people can be on that one computer, and they can do things at the same time. But there were still a lot of limitations to that, and the way it would do scheduling. Whereas now, like I could be on this computer, and like 5 other people could be on this computer, and like the computer wouldn't care. 1971, Intel gave us the first microprocessor. 1970s, microcomputers that were capable of microprogramming and using the microprocessor paved the way for personal computers, right? So microprocessor, things that exist in our laptops, super cool. And then 1980s, personal computers and competition between Microsoft's MS-DOS and the Apple Macintosh facilitated the rapid development of innovation in the operating systems, trying to one-up each other all the time. For bonus points, can anybody say who wrote the first compiler? Do you know? Yeah, Hopper. Admiral Grace Hopper wrote the first compiler. Yeah, I know. It's a fun fact. So why do we want to know about operating systems? So system level exploits require knowledge of those systems, right? Those operating systems. A lot of times that's memory exploits. The stuff that the Binex group is doing are those memory exploits. And then privilege escalation. So if we want to escalate our privilege, we have to know how we can manipulate the operating system to give us that higher privilege. Rootkits, those are kernel level applications. So the kernel, we'll talk more about that, but it ties deeply into the operating system. And then keyloggers, they're drivers. Drivers get plugged into our operating systems, right? We have drivers for our USBs, we have drivers for our internet, we have drivers for our mice, stuff like that. Cool. Operating systems, essentially, right? They're the layer in between the applications that run on our computer and the hardware. They provide an interface that communicates between the two. It has become more and more a suite of services, essentially, and tools, right? So now when you get Windows, you don't just get the Windows operating system with nothing on it, but you get a bunch of extra stuff. You get drivers with it, you get Microsoft Edge, you get, I'm trying to think what else you get. Normally it comes with like Windows Defender, stuff like that, right? So operating systems have expanded to not just be this interaction, this interface, but like everything that a computer could need at a base level. All right. So there's this thing called a bootloader. It starts the OS and initializes the hardware. So when we start our computer, it doesn't start the operating system, right? When we turn it on. When we turn it on, it starts our bootloader, and then our bootloader spins up our operating system and all the processes that it requires. It's generally included in our BIOS, which is the basic input and output system, or the board support package. So our bootloader is included with the BIOS, and the BIOS come on the motherboard of the computer. So it's deeply integrated into how the computer actually runs. So the kernel, I was saying that we talked more about this. So essentially, the kernel is the underlying fundamental structure of the operating system. So it's interesting because, like Windows, for example, their kernel is like tied to their operating system. There is very little separation between the two. Whereas Linux, the kernel, you have the Linux kernel, that's what it's called, and then distributions take the Linux kernel and they add their own things onto it. So the kernel is kind of like this separate concept for Linux, whereas Windows, they have a Windows kernel, but it's a lot more integrated with the operating system. And the kernel itself is what interacts with your CPU, your memory, and your devices. And then it goes to the applications. And that whole process is like your operating system, essentially. So kernel handles process management, memory management, inter-process communication, and system calls. I'm trying to think. So inter-process communication would be like one process talking to another process, right? So like my web browser talking to like my text editor to like download something, right? Like that's that inter-process communication. Except for it works at a much higher level, much more quickly. It also does file management, I/O device management, so and network communication services and protection services, right? So this is how the kernel handles storage devices, USBs, mice, keyboards, all that stuff is handled by your kernel. The kernel does not handle user interfaces. So the GUI, which is like when you log into Windows, you have that GUI. This is a GUI. And then you have a CLI, which is command line interface, which is what we've been working with, right, through the web browser. And then eventually, once you guys got your VMs, you started working with those. The kernel does not handle that. That's handled by the upper operating system. And the user interface is also known as the shell. And so that shell is what allows us to input commands to interact with our kernel, right? Because we can't interact directly with the kernel unless we are using code or we use the commands in our shell. And then the shell also allows us to interact with other applications in our operating system. Any questions so far? Okay. So command line interface versus GUI is a nice picture. It's really old, but these are both Windows. I think this is like Windows XP. Yeah. Yeah, Windows XP, and then this is the command prompt. Command prompt is weird. Yeah, Windows XP is also weird. Runs on some of our submarines still. Okay, applications. So applications can exist outside of the kernel and must communicate with the kernel to access hardware that it manages, right? So it has to communicate with the kernel to access the CPU, the RAM, storage devices, I/O devices. That all has to be done by communicating with the kernel. So the kernel has an application program interface, an API, that it says, hey, communicate with me through this API, and I'll do what you need me to do through those. At the lowest level, those are called system calls. So when we write programs and stuff like that, in like C, for example, the C programming language, we use a lot of system calls. Or we use higher level calls that always go down to system calls. So if it's communicating with the kernel, it's always going to do a system call. So for example, if I'm trying to read something in a program, it's always going to do the read system call, like at the lowest level. And if I'm trying to write something to a program, in a program, it'll always do the write system call, no matter what. It's always going to go down to that lowest level, which is really cool. So there's this idea of application modes. And I would say it's very similar to like administrative versus a regular user. So you have user space modes, and these are applications that users interact with via GUI or CLI. And these are applications that we're used to seeing, like Google Chrome, Firefox, stuff like that. The things that you see every day. But then there's also things that are kernel space mode. So these are applications that operate in kernel space. So that means that you normally run at a higher privilege level, and they access low-level things like our CPU, our RAM, stuff like that. And these are normally things that you don't see. So modules that come pre-installed onto your computer, power management, Wi-Fi, brightness display, things like that, that like, you see, but like you don't necessarily interact with the same way you would Google Chrome. Rootkits run in the kernel space, which is why they're super dangerous and pretty undetectable, because there's no really accounting of what's going on. I mean, there is an accounting of what goes on in the kernel space, but like you can hide it pretty well. Types of kernels. So this is important. There are monolithic kernels. I always find the word monolithic funny because it just sounds old. But this is like a classic kernel. It contains all the code necessary to perform all the kernel tasks. It contains all the device drivers, and it loads and unloads modules at runtime. So these are the things that are running in Unix, Linux, Windows, Mac OS, iOS, right? These are our basic kernel. I like to think of the kernel too, like it's like a popcorn kernel, because like everything else, you have that one kernel, and then when you turn the computer on, it's like turning the microwave on, and everything else pops up around it. I don't know if they meant it to be like that, but my brain's stupid, so yeah. And then you have a microkernel. So this is an archaic but good idea with many benefits. I would say it's less and less archaic. It's made somewhat of a comeback for multiple reasons. But basically, it does the most basic things that a kernel should do, and then it relies on the operating system to load on additional drivers and modules for it. There's a lot of benefits to it in terms of security, because everything's not running in kernel mode. But it's also harder for the devices to communicate between each other because it's relying on the operating system having figured that out. And so it's not running at such a low level, so it's not as quick. So micro versus monolithic. Monolithics are faster and less code is required, but microkernels are smaller, they are more secure, they're crash resistant and stable, and they're easy to modify and update. But they are slower. That's just like the simple fact. And yeah, it came out in the 70s, heavily researched in the 90s. Like I said, for certain systems, it is making a comeback. I cannot remember off the top of my head what systems. A lot of embedded systems started using them recently. Yeah.
So the big push for microkernels is primarily coming from China. So most of the Chinese operating systems that you see, so if you ever deal with Harmony OS or any of the stuff coming out of Huawei or that group, it's all going to be running on microkernels. So China has heavily embraced microkernels, And so if you ever have to do any development against China,
You gotta know microkernel look. So what happened to the microkernel? Blah blah blah. The microkernel technically like isn't gone completely. They also have these hybrid kernels. So this is interesting, right? So this is our monolithic kernel, where it's everything that it needs, and then it interacts with our application layer. And then microkernel, it's hardware, and then the basics of the kernel, and then all this runs into in the user mode. So everything that ran in kernel mode over here, besides the basics of memory management and scheduling for processes, now runs in user mode. And then you have a hybrid kernel, which is kind of like the best of both worlds, quote unquote, where it takes the things that really do need to run fast and puts that into kernel mode. So like application IPC, so that inter-process communication, that needs to go fast. And it'll go fast if it's in kernel mode. And then device drivers, that's best if it's in kernel mode. But then it takes like things like file servers and the Unix server, and it moves it up to user mode, and that'll move a little bit slow. So, like we said, microkernel is not completely gone. China uses it a lot. And then there's this idea of the hybrid kernel that gets used as well. Okay, so we're going to breeze through this a little bit, process management. So essentially what you need to know is that the operating system manages processes for us. So those processes, if you look at the task manager, you can see all the different processes that are running on your computer. So it manages how Google communicates. For some reason, it gives Google Chrome like 8 gigabytes of RAM all the time because it's malware. Does signal handling, processes, and thread creation, termination. And then a part of that process management is that inter-process communication. Talking about this, what a process is, it is an instance of a running program. So you could have 3 Google Chromes running, and each one of those is a different process. There's things that identify a process. So there's this idea of this process block, and it has like a PID, which is the identifier, and then all the information about that process is stored in that process block. It's process tables. So processes are normally created with a parent-child relationship. So we were talking about the bootloader, right? And how the bootloader spawns the operating system. Essentially, all the processes are spawned from the parent bootloader, and then processes from there are spawned, such forth. So like if I run a program from my command line, and then I check to see if who its parent is, its parent should be the shell that I spawned. And so they kind of have these parent-child relationships. It's very interesting. Zombies are processes that are no longer executing, but they're still taking up resources. It could just be that they're in the process of getting deleted, or it could be that they didn't get deleted correctly, stuff like that. And then orphan processes are processes that it's executing, but its parent isn't. Scheduling. The operating system's super smart, and it knows how to schedule. And there's a lot of arguments about the different ways that we should schedule and benefits about that. It's not really important right now. There's different things that take priority. This is also debated. These are all decisions that programmers make in designing the operating system to say like, hey, this process should take priority this way. This process should take priority this way. Interrupts. There's different types of interrupts. There's a hardware interrupt and there's a software interrupt. So I would say like a good example of this is like if I do control the task manager and then I like close the process, it's like that's a hardware interrupt that's like stopping it. And then like if I program a stop into like my program or something like that, like I code that, that's like a software interrupt. Okay, and then the next thing that the CPU does is memory management. So this is going to get super into the woods, and so we're not going to go very deep into it at all, just like processes. Yes.
Sorry, can you go back like a slide? I just kind of want to like look at the quiz questions.
Yeah,
see
yeah,
if
yeah,
I
yeah.
understood it. Mm,
A lot of them have to do with processes. So that's why I skipped over it.
Conclusion. I don't get it, but okay.
Don't worry about the processes thing right now. The idea for this is that you understand what an operating system is and understand what a kernel is and understand that it basically manages everything for the computer, right?
Can you give me like the stupidest definition for a kernel?
It is what manages like everything about your computer.
It's the bridge
low-level
between
code.
your hardware and your software.
Yeah.
So like, if you want to do anything with software, the kernel is going to make the hardware do it. So your software wants to add like 2 and 2, right? Your CPU is going to do that through the ALU, but you're not going to program like, all right, so we're going to send these couple of bits straight to the CPU, and then it's going to go over to the ALU. You're going to have the kernel go and make that call to the CPU. So the kernel is like that bridge between what you're trying to do with software and what the hardware on your machine's doing. I think that's
the easiest stuff.
Thank you.
Okay. Memory. So essentially, you have your CPU, right? And on the CPU are these things called registers and caches. And these are the quickest memory that we can access. That's all you need to know for that. All right. And then outside of that, you have main memory and secondary memory. Our main memory comes from our RAM, which is our random access memory, which is non-persistent, so it clears itself every boot. And then you have secondary memory, which is our permanent memory, and that's things like our hard disk drive, where it has like the spinning disk, or like our SSD, which is a solid state drive, which does the same thing that a hard disk drive does, but instead of a actual disk where it's like tapping a point to access a bit, it's using software instead. So fast memory is registers and caches. Slower memory is RAM and SSDs and HDDs. Yep. Okay. Yeah, that's it. So, long story short, right? CPU and kernel are a bridge between applications and hardware, software and hardware, right? The kernel is that main connection, and it provides us a API, an application program interface, to tell the kernel, to have the kernel tell the hardware what it needs to do. But we do not make the individual decisions of like, hey, change this exact bit. The kernel will manage that for us, so it's easier. And then the operating system is everything else that gets wrapped into it. It's that suite of tools and programs that come automatically installed for us, right? So when you have Windows, you have Microsoft Edge that gets loaded with it. You get a file explorer that's loaded with it. You get the recycling bin that's loaded with it. When you have Ubuntu, you get things like the GNU terminal. You get the software center. It comes with Firefox on it. And so that's what that operating system is. It's tying in the rest of the applications that it automatically downloads for the computer to work. Any questions? Cool. All right.